Happy Halloween, and welcome to MLBBQ. Today is a Halloween special for MLBBQ, and I'll be presenting a paper from Moonshot AI, another Chinese lab, called Muon is scalable for LLM training. So, at the start, who is Moonshot? Moonshot is a Chinese firm. This time it's not a hedge fund, and they are seeking optimal conversion from energy to intelligence, supposedly from their website. They have made a couple models, of which TBK2 released earlier this year is a 1 trillion parameter model, and it is the current best open source LLM. It tops out on every single benchmark, and it rivals closed source models on a lot of benchmarks also. And in my use cases, it's arguably the best LLM for a lot of things I do, like say theorem proving. Here are the benchmarks. So Sweetbench beats out OpenAI. I believe that's GPT 4.1. GPT 5 might be better by this point. Beats out DeepSeek by a lot. Beats out Quen by a lot. Beats every single model open source. Sometimes even beating or rivaling Opus, like on AceBench. It's state of the art on IME, and it's also state of the art on GPT-2A Diamond. So many benchmarks completely saturated. And they also made many more models, like Kimi Researcher, Kimi Audio. Kimi Approver is a very interesting one I might do a talk on in the future. And today we're talking about Muon, or their application. It's a speech to text model, or text to speech model. Yeah. And they also made Kimi Approver, which is the state of the art model on the mini F2F benchmark, which is a benchmark for formal theorem proving. It beats everything else by a lot. And if you've ever touched Lean before, you know that this language is very hard. So getting this actually working is much more complicated than just fine tuning on a bunch of traces for Lean. They had to create their own RL harnesses. So it's a research/infra team similar to DeepSeek. And the difference from DeepSeek, though, is that they have a lot more math people. And so in DeepSeek Prover v2, the Lean expertise that they had on the team wasn't completely up to par. And so a couple of theorems that the model presented got passed through the checker, even though it shouldn't. The model kind of bypassed a couple of requirements by using tactics that had side effects. The tactic in question was apply question mark.
Are you talking about DeepSeek now, or
DeepSeek Prover v2 in comparison to Kimina?
Okay.
Yes, they're much more careful about their data. So here's the actual Halloween special. We are going to actually be deriving Muon today, and this is going to involve probably 30 minutes of linear algebra.
Yay.
To assist with it, I've come up with the intuition cat, which translates the Greek into conversational English wherever it might be necessary. This is heavily based on the blog Deriving Muon from one of the original authors of Muon, Jeremy Bernstein. So, motivating problem. Linear layers dominate neural nets, especially transformers. If you look at a transformer over there, everything besides the input and output embedding layers is a linear layer. Besides, with parameters, I mean. Feed forwards are linear, MHA, linear, an actual linear layer. Like everything's a linear layer. Even MOE layers these days are also linear. So, given that, right, and given that also we obsess over norms for activations, like say RMS norm, batch norm, all those things. We constrain the norms because there is numerical niceties about keeping your numbers well behaved in terms of norms. But we ignore how the weight updates affect the activations. And so there's a disconnect between the geometry of the outputs and the geometry of the function that produces them. So how do we solve the problem of there being a disconnect between the geometry of outputs and the function? Well, just like activation norms bound function, activation norms bound activations, what if we can bound how much a weight change affects the activations, i.e. in the optimizer? So if we were able to bound it in the same way that RMS norm makes our activations behave much more nicely, we will get consistent behavior across initializations. So we might be able to initialize two different models of completely different scales and get similar performance, like predictable performance. We might also prevent instability, bounding the change in activations as a result of weight updates makes it so that your models don't have random like spikes in activations after doing a gradient update. And so it makes everything much more well behaved. It also improves gradient flow because it can't underflow or overflow. And everything that the original that RMS norm or the different norms offer to you can be translated over to the case of fixing the geometry of the optimizer itself.
Is it like, are you trying to bound the gradient now?
We are bounding the change in activations with respect to a change in the weights.
Which is?
A change in the weights is derived from the optimizer.
Oh, which is the gradient?
Which is the gradient. Yeah.
Okay.
Yeah. And so, given that we want to do this, what might solve it? Well, we can translate the sentence. We want an optimizer which bounds how much shifts in the weights affect shifts in the activations. We get this expression. We minimize over change in the weights. We minimize the inner product between the gradient of loss with respect to the weights, as well as the gradient, the change in the weights, subject to the constraint we just mentioned, which is bounding the change in the activations.
Change in activations in response to what?
Change in activations in response to, the only thing changing here is delta W. Yeah. So we minimize delta W such that this guy is still bounded by some constant. Yeah. Okay. So the min term, the inner product thing is just a definition of an optimizer over loss.
Wait. If you set delta W to 0, then change in Y passes through the constraint, then you're done. You always satisfy things. How do I avoid that?
That's obvious. That's the trivial case of the orthogonal. Like you can always set delta W to be orthogonal to the gradient, but that's not what you want, right?
Or 0.
Or 0. Yeah. Those are trivial cases we ignore. We want
protect against the process falling into them because that's easiest thing.
Yeah, there's a bunch of load bearing extra constraints here that weren't specified in the blog, but yeah, those are also what you should mention. It's like this shouldn't be 0, and also this shouldn't be. There should be a bounding condition to make this not orthogonal to the gradient. Okay, so we have this delta y and we have delta w. How do we relate y to w? So the question is, how do we parameterize delta y under some norm? So this double bar means norm, and this is RMS norm in particular, in terms of delta w, which is obtained via the gradient. But we have that y equals wx. For a linear layer, it just means taking the vector, multiplying by matrix, you get the output. We can subtract y from before and after we apply delta w to w. So it's delta w plus w, and then the before is w. So we just take after minus before equals to delta. So delta y equals delta w times x. And then we can take the norm of both sides. So we take the norm of delta y, and we also take the norm of delta w times x. This is just algebra. Any questions? Feel free to interrupt at any time. This took me 5 hours to derive for myself again. So if at any point you get stuck.
Does anything change if we consider nonlinear stuff?
We only look at the linear layer itself, and so we don't have to care about the nonlinearity. Yeah. So, but there's a weirdness thing here. This is a mappable. What is a norm of a matrix mappable? Right? We usually think of norms as a way of taking the size of a vector, and one such norm, RMS norm, lets us quantify the average size of entries in that vector. This is RMS norm. It's just that. And it gives us the norm, the average size of entries, as opposed to, say, like L1 and L2. They would give you the average size of the whole vector, which is different. Yeah, because there's this term, in this case it's n, which is the size of the vector itself. It's just normalized L2.
The length.
Yeah. So Again, what's the norm of a matrix? Well, given that we know how to take the norm of a vector, we can maybe define an operator norm for a matrix by seeing the impacts of the operator on the norm of the input or the norm of the output given the norm of the input. So we relate the norms of the input to the output. And so we can define it, norm of W, or this is called the operator norm of W, is defined as the maximal change or the maximal difference, the ratio between applying W to X against X, right? And then you can replace in the definition of RMS norm on both sides. And then you can factor out the non-varying element, which in this case is root D and D out. And in here now you only have this term. So max, given that X is not 0, of the L2 norm of Wx over the L2 norm of X, which has an identity being the spectral norm of W. The spectral norm is the the spectral norm is just the largest singular value of W. Okay. Anything? Okay. Yeah, this is just some identities. Okay. So how does this get us the norm of the matrix update? So the operator norm gives us literally what we want. Since it's a supernum, this is a max over X. It gives us an upper bound on the matrix update, and by consequence, an upper bound on the change in the activations. If we go back to the slide describing what we want, we wanted this delta y guy to be bounded by some constant. So this is kind of shaping up to be what we want. Okay, yes. And so we can restate. Norm of delta y is equal to norm of delta wx is less than or equal to the operator norm of delta w times the RMS norm of x. That makes sense. Okay, and that's our original constraint that can be restated. We're minimizing the inner product using gradient and weight update subject to the operator norm. So we're bounding the operator norm to be less than some constant. This process is called dualization, which means looking at the problem from the perspective of the function as opposed to its inputs and outputs. So usually we look at the problem of activation normalization from the perspective of the activations themselves, but we can also take a look at the dual perspective, which is looking at the function which produces the activations. So now we solve the minimization problem. We know that every matrix has a singular value decomposition. In the case, it's just U sigma V transpose, where U and V are orthogonal matrices, the singular vectors, and sigma is diagonal containing all the singular values. The solution to our constrained optimization problem equals this. This is magic, which I'll get to in 1 second, but this process is called orthogonalizing the gradient. And I will clarify that this derivation is way, way beyond the scope of this talk. It's actually scary mathematics. I had to kind of work through it, but it's about 6 pages of derivations, and it involves some stuff that you definitely have not learned if you haven't taken like a functional analysis class, which I have not.
But, what are we talking about? This too small print. Let's look at.
Can everyone read this font?
No, this one is okay.
Okay.
Wait. No, but this one is not.
Yeah, this one is not. This one we're not walking through this. Yes.
Yeah. So what is this about? How to solve that minimization problem? Okay, you're going with this VT, and what are you doing? Exclusion of our constraint. You're dropping the eigenvalues completely.
Yes, you are orthogonalizing the gradient. You're setting all of the singular values to 1.
But then you have to do that.
You don't. That's a trick. You don't actually have to do SPD. Yeah. You can implicitly orthogonalize. With a technique later. So the actual heart of the problem here is, orthogonalization. What is orthogonalization? We're comparing the gradient to the update. So the gradient is decomposed into SVD like that, and the update is parameterized like that. Orthogonalization, we keep U and V, so the update is pointing in the same direction as the gradient, but we normalize all magnitudes. So every direction that you step in, not necessarily that all the magnitudes are one, but it's more so that all of the important directions are normalized to direction one. So you saturate the gradient gives you a signal for where to move. Setting delta W to be equal to UV transpose essentially saturates that information to the
I don't get it. Like you always move diagonally in this sense, right? For a vector.
What do you mean diagonally?
In the space of all possible moves. Like you equally have almost like equally have the. Well, I must be interpreting something. Like singular values give you a spherical direction, right? And any direction is same way, equally likely, whatever you prefer. But that means if you are in n square dimensional space, you move diagonally. In the like you measure two-dimensional space, one on x, one on y, you move diagonally.
One on x, one on y, you move diagonally.
Yeah.
Versus
moving in some useful directions. Like if you're updating all weights equally, your gradient.
Yeah. I see what you mean. Yeah, it's not that you're moving in all directions with uniform width. It's more so that all the you step with the same magnitude in all the important directions, because that's what the singular values tell you.
Oh, you threshold.
Yeah.
The threshold. Okay. But still.
I don't think you're walking diagonally though.
Well, in that subspace, in that kind of like, even if you have say a 2D plane, 3D, then same thing applies. You move in x and y direction with that plane, so you kind of working diagonally with that. So if everyone is like this, so then it's the middle of the column. There is sign also that is. Okay, anyways, let's go. I'll think about it for a minute.
So why does orthogonalization solve the problem? The orthogonalized matrix UV transpose has operator norm equals 1. And so the spectral norm is 1. And so our update saturates the constraint. It has an exact value that is equal to the normalized operator norm. And this term over here normalizes such that for all inputs, it basically cancels out the differences between dimensions because RMS norm normalizes for the dimension of the vectors. And so because it maps from one space to a different space, you have to take that into account. This solution maximally aligns with the gradient direction. It moves in all the directions that the gradient points to, and it treats each direction equally. So this is called a democratic update.
This is weird. I don't understand exactly my problem. Why is it good?
Because it reminds me of this formal gradient idea when they were using like inverted gradient, which is approximately in the right direction, but not quite.
Natural gradient?
This is related to a natural gradient design. Yeah, it's from the same field, from geometric information theory.
Okay.
Yeah. So your question, but isn't SVD expensive? Full SVD is about cubic. Yeah. And so for large void matrices, it's basically impossible to do. However, we have Newton-Schultz iteration, which
you're going so quickly where you didn't pass. I can't see what we stay.
Yeah, this is just time complexity. It's not that hard to derive. It's just triply nested for loops. Okay, so Newton-Schultz iteration. The key insight is that odd polynomials commute within SVD. So we have that for odd polynomial, which are just polynomials where the degree of and a matrix G, which is equal to which has some SVD decomposition. Applying P to G is equal to applying P to only sigma. You don't actually have to apply it to the decomposed matrices, which means that if you apply the polynomial to the whole matrix, it is equivalent to applying it to just the singular values while keeping U and V intact. Which is
You
what
still have to compute P.
No, we don't, because we can just apply it to G. By applying it to G, we are implicitly applying it only to sigma.
Oh, okay.
Yeah. So we can skip that trick, and this is a linear algebra factoring trick. Newton-Schultz can achieve orthogonalization. So if we use this special odd polynomial, where the coefficients are 3/2 times x minus 1/2 x cubed, if you apply this repeatedly to a value x, it approximates the sine function. And the funny, thanks, Mom. I know you love this.
No, but I mean, yeah, it's a universal string compute value.
Yeah. And the funny thing is that the sine function applied to sigma orthogonalizes it. It normalizes everything to 1. So this is from 1993. It's a German paper, and the nice part is that even though the derivation is super long, you can just kind of trust that the results work, and you can also validate this empirically. So Newton-Schultz in practice, how do you perform this? Well, you have a matrix G, which is the gradient or momentum. In practice, people use momentum. You normalize so that all the singular values are less than 1. This is a constraint on this convergence. It only converges to sine if the singular values are less than 1, which you can easily do because you can normalize. But this is load-bearing. You have to get a spectral norm estimate, which may or may not be expensive. So you normalize by the larger spectral norm, which brings it down to less than 1. And then you iterate the cubic function 5 to 10 times. So you just loop it. And then you multiply it by exactly this polynomial.
Well, yeah, spectral norm. So you do your
Power iteration.
Yeah, power iteration,
Yeah.
and that's still expensive. Okay.
But it's only using matmos.
Yeah.
And it's easy.
Yeah, I mean, it's matrix vector.
Yeah, it's matrix vector, and it's very, very cheap to do, so no expensive SVD required. That's the only intuition cat on the right
Yeah,
hand
matrix
slides.
vector is quadratic.
Matrix vector is quadratic. Matrix is
Still expensive. I don't know why it's not expensive.
it's not as expensive as SVD.
Yeah, of course.
Yeah.
But, I mean, if I don't do anything, just do gradients and SVD.
Well, there's a reason we do it, but I'll go into that later. Yeah, so Muon, the algorithm is now discovered. Does everyone see why Newton-Schultz kind of ties into it? Like, because the original stories that we wanted from over here, yes, we wanted the bound on delta W, the normal delta W. And we could only get that if we have UV transpose.
Yes, because identity.
Yeah.
Sigma to identity.
And these are constants, so you don't have to care about them. So we have to find this guy, but we have to find this guy, which is derived from the gradient. And that's the SVD decomposition of the gradient. And Newton-Schultz is a way to get UV transpose without having to do SVD. Yeah. And so the algorithm in practice looks like compute the gradient, delta WL, or momentum. This is just backprop. You orthogonalize by a Newton-Schultz iteration, which is the algorithm we just looked at. We scale the result of that by eta times the normalized square root d out over d in. and you update the weights. It costs roughly 5 mat moles per update. And the results of this algorithm is a principal optimizer that controls activation changes. So it doesn't just change the weights. It also you can manipulate how it affects the activations. The other best part is that it can transfer learning rates across widths automatically. And this can converge faster than Atom in practice. And the proof of that is in the paper that we'll be discussing today. So yeah, the general lesson is that by working backwards from some mathematical constraint, we can obtain a method which achieves it. So in this case, we wanted something that took into account the norm of the activations. And specifically, we had to look at the operator which produces it, which in this case is a linear layer. And by working backwards from that constraint, we can derive an algorithm that gives us that optimizer. So this is a very nice algorithm for discovering new optimizers. Some caveats. For stability, orthogonalization happens on the momentum of the gradient, not the gradient itself. Momentum is just the running exponential moving average mean of the gradient, which means that you have to keep one extra buffer, but so does Atom, so we're fine. Newton-Schulz only converges to singular values are in 0 and 1, so we have to pre-normalize. This is part of this Newton-Schulz in practice. You have to pre-normalize it in advance. The NS iteration count. So yeah, Newton-Schulz iteration converges to sign, but after how many iterations? In practice, it's been found to be 5 to 10, and this is through community effort. So people ran a bunch of runs in parallel and then submitted their results to a repo, and then we found that 5 to 10 was best through empirics. Same thing with the Newton-Schulz coefficients. These were also found empirically, 1.5, 0.5. Other tricks, LR warm-up, gradient clipping, mixed precision can be handled separately from the optimizer. So there's no reason to bake them directly into the optimizer.
So you do that for each matrix because you're treating, it's not the entire gradient of all parameters.
Yes.
You treat them independently for each matrix.
Yeah.
And each matrix is not that much.
Yes. Yeah. So yeah.
And you can do that parallel after you have computed the gradient.
Yes.
You can compute all of those matrices.
I think in practice it is still better to do it sequentially along with the backprop, because it's easier to shard it across in parallel as opposed to having each worker work on a separate layer because bubbles.
So the top layers computed first.
Yeah. You just compute it straight like that.
Yeah, because your updates they don't hide
Yeah, it doesn't necessarily have to be. But I think in practice for scheduling reasons, I mean, I don't think this is completely true forever, because you can definitely design a model that has uniform gradient size across, and then you can do full backprop and then broadcast the optimizer updates. Yeah. But yes, Muon in practice. So now we finally look at the paper. Muon is scalable for LLM training. This is from Musha AI plus one person from UCLA. Empirically, Muon is 2x faster than Atom on transformers, and in their case, they're training a pretty box standard. Specifically, they're training the DeepSeek V3 architecture.
Faster to convert or faster for iteration?
Faster to converge in general. This is wall clock.
So to convert.
Yeah, to converge.
So less steps.
Less steps. Boom. Okay, so we talked about the practical tricks that we have to use, and the first one that they actually have to use was weight decay. Muon is better than Atom W on a scale shown by Keller Jordan on the GPT speedruns, but they also found that adding a weight decay mechanism into Muon empirically also made it better.
So I have a question.
Yes.
So why do we need to scale Muon? What is the issue with it right now? Why it cannot be applied on the lines?
The issue for scaling is primarily engineering and partially also numerics. Say for an optimizer like Atom took a non-trivial amount of effort to parallel or to scale to thousands of GPUs. because like unlike gradient descent, regular gradient descent can apply directly just by multiplying by some learning rate to the weights, and so you can do that in place. But Atom has many tricks that are complicated to do state management of, like say for momentum. If you have momentum, then you have to keep a secondary buffer alongside your gradient. So you have your model weights, the gradient itself, and then the momentum. If you're sharding your optimizer state across all these GPUs, doing the momentum calculation every step is not trivial. Because how do you do that broadcast, right? But at every step,
it's just a sum. That's the problem. Keep it split in. I don't see the problem. There's no mixture. There's no mixture. Momentum is just accumulated gradient.
Yeah, but how do you do that accumulation?
You have the third buffer, so keep accumulating.
Right, but like the communication to do that accumulation
keep
is not
the
easy.
buffer where the gradient and parameters are. Layers, like split it across layers.
But each GPU only has part of the momentum and gradient tensors. They don't have, no GPU has the entire gradient.
Yeah, but they don't need. So there is no mixing.
Yeah, but in effect, you do like a ring all reduce, but that's still not entirely trivial. Like,
let's say if you do like fair scale, if you have 8 GPUs and 8 layers, and each layer is computed by a GPU, then GPU doesn't need to wait until the other GPU, in a sense. It has all 3 buffers that it needs.
It has all 3 local buffers.
Yeah.
But in accounting for
only the gradient propagates. That's it. But you have to do that for SGP. Once you've got your local gradient or your local parameters, you just accumulate them, and that's your accumulation buffer. And that's all you need from an atom.
Does that work locally?
But there is no mixing. It's just a sum. Weighted sum.
Is it per scalar? If it's per scalar, it should be fine.
Yeah. It is per scalar. That's the point of all of this. So something else is at play.
They do have an algorithm for Muon that details the momentum trick later. But yeah, scaling is not super easy, especially for more advanced like sharding tactics. Like anyone here ever use deep speed? Yeah, like FSDP2. Most people use DDP here. Yeah, the DDP is super simple, super nice. Deep speed has like a bunch of async stuff where you do some, the word is compute and communication overlap. So you try to do weight transfers at the same time as you're doing some computation. And there's a bunch of tricks for that. And minimizing the bubbles where you're either only, or you're waiting for data to do computation is the task. But yeah, it's not easy in practice for the scales that they were doing this.
This Canadian company sent you the company that does do that. That's the GPU can parallel to inference and gradient descent, and so you utilize everything efficiently. I mean, it's an engineering difficulty, but people do that.
Yeah, it's primarily an engineering difficulty. There we go. So we have empirical. So we have Atom W, worst. Muon without weight decay in blue. No, Muon without weight decay in red, my bad. And then with weight decay in blue, beats out by the end. So at the start, it seems like Muon without weight decay was performing better, but at the end it did better. I think the same behavior will also happen for Atom. So practical trick number 2. They changed the scaling. So the original scaling was, the theoretical is 1 over max AB. They found that changing this over to just the square root of max AB was better, and they have a proof of it. I didn't completely go into detail for the proof because it's pretty involved, but it has to do with the size of the matrix itself. Yeah, so when max AB is too large, that's MLB matrix, the updates can become too small. thus limiting the model's representation capacity. When it's too small, we treat each KB head in, this is their version of, or a modified version of attention, or in DeepSeek's version of attention, a separate parameter. The updates become too large, thus causing training instabilities and leading to suboptimal performances as well. So one of the assumptions in Muon was that the linear layer should be roughly, but that's not necessarily true for a transformer. The proper linear layers in the transformers are usually uniform in size, but the attention heads are also linear layers, but they're smaller by like orders of magnitude. And so having this, because the moment that you're transferring from your attention head over to your linear layer, there's going to be this huge gap in the input size and the output size. And so if it's too, if the differential is huge, if the number is huge, then the updates can perform poorly, basically. Go. Back to question number 3. We use it in combination with Adam. So uniform optimizers is usually the expected norm. You either use Adagrad, you use SGD, you use Adam. But in the case of Muon, because it only is proven to be optimal for, or not optimal, it's proven to be better for linear layers. What if your model has things that aren't linear layers? What if your model has embedding layers, which aren't actually linear layers? Or what if your model has comms, which aren't linear layers? In that case, you can actually fall back to Adam W. And so that's what they did, because the transformer has linear layers. Oh, what? Comms are composed of linear layers, but the operator norm is not the same.
It's a repeated thing.
But it's done differently. So if you look at the norms, they'll be different. It is a linear operation, but the linear layer that we're talking about.
Oh, what do you mean then by linear?
A matmul, yes, a strict matmul. Yeah. A matmul behaves like that because it has those specific.
Well, it's done by matmul as well when you.
Yeah, when you do the stride, but you're like overlapping a bunch of them, and then like also doing pooling at the end changes the norm and so on. Yeah, it's a
different way.
Yes, but that also points towards the direction of a future optimizer, which is what if you actually did the analysis of the operator norm for comps, and then you have your new optimizer and new paper. Yes, so this is the algorithm that they had to modify. So instead of only doing, so they did G, full gradients G, and you have data parallel partition momentum, data parallel partition parameters. And so first you do reduce scatter on G. Is everyone here familiar with distributed programming terms? You know what MapReduce is? Oh no. Yeah, so reduce scatter is when you accumulate a bunch of things and you take an average, for example, and then you redistribute that average to all the workers. So that's a reduced scatter. Yeah, and then
why are they not doing B-reduce, which is probably efficient, right? Why everyone is just doing this stuff, reduce all, gather all, reduce that? Is it because hardware is more
I think
optimized for that?
I think it's to do with the specific algorithm in question, like what specific operation that you're doing. Ring all reduces are better.
You don't need to do ring all reduces. You're not right. You go around the ring and you're done. You compute everything. So like you don't need to do all gather all reduce if you do this ring reduce.
I'm not sure why they do reduce scatter in the case of gradients. Yeah.
Maybe it's faster. I don't know.
Yeah, it's probably just faster. It might also have to do with the size of G. It might be that ring reduces are better if the buffer sizes are smaller.
Yeah, something like that. No, I'm not sure. This I forgot the library name from Uber that I demonstrated long ago. Linear scaling with GPU numbers, basically. It's kind of was almost like you install AGVs and it performs 8 times better.
Mhm.
It starts with H, but it's really good. And then like nobody people start using it really good.
It might also be the case that ring reduce is only optimal on uniform topologies. In the case of huge scales like this, you have different networking speeds between same node GPUs and inter-node. And so if you do ring, you'll get a bunch of bubbles while you're communicating across the node barriers. Yeah, but I think
I will look it up. I just wonder why.
yeah. Okay, so yeah, you can apply momentum to G using locally partitioned momentum M. Yeah, so you were right. You can do momentum update locally, and then you do DP gather. You gather G prime across DP into flow matrix G. So you need to collect the momentum into the flow matrix. There we go. And then you perform Newton-Schulz on G. So G here is no longer gradient. It is now momentum.
So where are like the singular values in this part? Because I remember we have to scale them to like.
It's handled implicitly by Newton-Schulz.
Okay, so line 8.
Yeah, line 8 right here. Newton-Schulz is actually orthogonalizing the matrix. Yeah, so it's applying the operation implicitly to the singular values
It's not
without ever.
orthogonalized. It's not. It's just messing with regular.
That's what it is. But that's what orthogonalization is, though. You're turning all the singular values to one.
No, so singular values to one is white. So
I think there might be.
yeah, you're not finding orthogonal components. That's the point. Orthogonalization is when you're finding U and V. They're orthogonal spaces.
But
Yeah,
you don't.
That,
You're just whitening. You're just setting everything to the same scale. Everything is eigenvalues. You're setting everything at eigenvalues, single values to one. And that's all you do.
But in doing so, you've turned sigma into identity, which means that you found UV transpose.
No, you didn't.
Well, no, not necessarily. Well, the if we orthogonalize the singular values matrix, that means they point in different directions, right? Or they're
No, you don't touch UV. You don't touch UV transpose. You only modify the singular values in the middle to make them all one.
Oh, I thought they had to be less than one, or
You turn them less to one so that the Newton-Schulz converges. And then after you iterate, they do actually turn all into one. Yeah. And so
just 1 second. So G is a matrix for one single layer, one single W times X, right?
Mhm.
And that one single W times X is distributed across multiple GPUs and nodes.
Yeah.
One single linear transform is computed across GPUs.
Mhm.
Because that matrix is so huge.
Is huge, yeah. It's absolutely huge.
For each layer.
For each layer.
For just a single one. So what is W size? What is the G? What is the embedding size for this matrix to be that huge?
We can look at the
Like what is like
scalable. We did publish the actual parameter counts or the mall architecture.
not entire number of parameters don't matter.
No, it's like per layer.
Yeah. You see what I just want to see one W times X. What is the W size? What is X size? Well, if you have okay. Oh no. For attention it doesn't matter, I guess. It's just all we're looking at is the embedding size. Is the G. That what affects the MLBs.
Where's the size? Hidden dim here.
What is it then?
2K.
just 2000?
This is
By 2000.
this is a scaling experiment. This model is only 1.5B, but they've scaled it up to over 1 trillion.
Yeah, so in this case, what is that 2K concept? What is the hidden dimension, the embedding dimension?
You don't say, that's so sad.
Yeah, because I'm surprised that this matrix, so you have 80 gigs of memory, right?
Mhm.
And this matrix doesn't fit in 80 gigs. Yeah, of course.
Oh no, it's because you're trading with insane batch sizes too. The activations are also massive.
But each element in batch size is independent of each other elements. You have this momentum and everything.
Mhm.
So if you go back to your 5 algorithm, I'm asking about why you is across, because your Newton shows iterates in the batch size, iterates only with one matrix. It doesn't work with the batch thing. You can parallelize, etc., but it affects eigenvalues of one sample in the batch. Like each sample in the batch is independent.
In effect, people don't care about that. They skip it. They perform new controls on the entire gradient matrix.
What is the entire gradient?
It's the accumulated gradient.
What is the dimension of G?
So they're not orthogonalizing the weights.
Yeah, they're orthogonalizing the updates.
Only the gradient.
Yeah, in this case, they're orthogonalizing the momentum, actually, not even the updates.
No, but it's the same as gradient. It's fine.
Yeah.
It's just a accumulated gradient. But what is the dimension G? It's a 2D thing. It's a matrix. When you apply Newton shows, you not applying Newton shows doesn't apply to 3D tensors or 5D,
Mhm.
whatever. It
Yes,
applies to 2D.
you accumulate the gradient across all batches.
That's
And in the case of a embedding dimension 2K, then G is going to be 2K. 2K by 2K.
tiny.
Well, that's for the scaling experiment that they did, but for the 1 trillion parameter model, if the 1.5B parameter model had dimension 2K, then 1 trillion.
So how does the trillion get there? Because your embedded dimension is huge now.
Yeah,
That's
embedding
how it
dimension is much huger.
Yeah, I wonder what it is. So that's how you're like, it's not number of layers or anything. It's just like, oh, blow it up, make it fatter, basically, right?
That's most of scaling.
Add more embedding dimension.
Yeah, when people talk about scaling language models, primarily width, not depth.
Yeah, but that's weird, I think. So I was like, yeah, okay, I'll ask for flexity or whatever. What is that G size so that it doesn't fit in 80 gigs?
Mhm. And then once you found the Newton-Schultz iterated matrix, you discard the rest and you only keep the local partition U. So the one that has the exact same indices as your local weights. And then you apply the update rule, which can be applied locally. That was
you lost me there.
the update rule is this thing, 3 and 4, which is just multiplying by a scalar and then adding to your weights.
Yeah, Newton Schultz is also local, just for your local momentum. You don't care about any other layer or anything momentum.
So,
Yeah, there's no mixing. It's an accumulation.
no, it's G times G by itself. You have to do the full thing.
What is that? What is this? Iterate the cubic.
This is you're iterating this polynomial P3, which requires the full matrix.
No, but your full matrix is only for your because your matrix.
Yeah, for the gradient matrix itself is huge.
Okay.
Yeah, and then after 2 has to be done globally, and 3 can be done locally because it's just multiplying by scalar and adding to your local weights.
Okay.
Yeah. Okay.
We have 5 minutes,
No.
but we can still order.
How does it compare to Atom? In terms of memory usage, it only uses one momentum buffer, while Atom W has two. Therefore, it's half. Right. The additional memory on top of SUD, it has lower communication overhead compared to Atom because it has one fewer buffer. Latency. Distributed Atom because it introduces two additional communications and requiring running Newton shells. Newton shells is inherently sequential, whereas the gather and like momentum calculation for Atom can be done in parallel. So it has higher latency, but yeah, it cancels out in the end for end-to-end trading time because of the added efficiency of Muon.
Okay.
So why Muon? To restate, it's 2x faster than Atom. It's also easier to tune the learning rate, and so it exhibits learning rate transfer, where if you scale up your embedding size or the size of your linear layers, the same learning rate applies. So you can tune the LR on a very small model and then trust that same LR will now work on the scaled up version of your model, which is invaluable in practice because that means that you don't have to run sweeps on your insanely large model.
So what is a sweep?
Like hyperparameter sweep for LR.
Yeah. Okay.
Mike, is this maybe because like the matrix norm is 1? Do you think it's this?
Yeah. It's related to the orthogonalization.
Okay.
There's a different derivation. Mu P is an initialization scheme that exhibits sort of learning rate transfer. Mu P though is generic over all hyperparameters. That's a different paper from Greg Yang, the optimizer guy working at XAI. Tensor papers, great paper. So also in comparison to Atom, it doesn't really have hyperparameters besides one. It only has the Newton-Schultz iteration step, and that's hard coded to 5 because we found it in practice to be fine for 5. So no more like beta 1, beta 2, whatever for Atom. No need for tuning. And so one complaint that people have about Muon is that when you properly tune the Atom baseline, it performs similarly to Muon anyway, so why would you even use Muon? But the thing is, who wants to do Atom tuning? Like, who here knows how to tune Atom? Right? Like, no one wants to like spend their time doing that thing, and it's incredibly expensive at the high scale because the hyperparameters do not transfer across sizes, and so you have to run insane sweeps, like thousands and thousands of dollars of sweeps, just to find those hyperparameters. Whereas with Muon, you can just kind of hit go. After you found LR, which you can do in the smaller model size in the first place. This implementation is from NanoChat, so shout outs to Karpathy for tossing this in. And it's also state of the art on NanoGPT. So the original LLM.C was from Karpathy, and that's the curve. And if after people did some tweaks, it got to here, and then adding Muon, you get to all the way over here. And this is for eval and train and eval. Top curve is train, bottom is top
it's
is
a larger model.
Huh?
It's a larger model.
So larger. No, this is the same size. Oh yes. Yeah, you're right. My bad. Okay. And also it works on scales past 1 trillion parameters. So it's been exhibited. It was used to train Kimi K2, which is so far the largest open source model that's performance trained. I know there's Megatron LLM, but Megatron LLM sucks and no one uses it. This one is actually practical and you can use it today. So why not always use Muon? Well, one reason is because you literally cannot. It's designed for linear layers, and so if your operator has a different norm compared to linear layers, you can't really use it in practice. The Newton shells will throw it off center. It doesn't beat Atom on fine-tuning Atom pre-trained models. So if your model is pre-trained using Atom, using Muon to fine-tune doesn't work as well as just using Atom. However, Muon plus Muon is actually fine. So if your model is trained using Muon, you can continue fine-tuning it using Muon. And interestingly here, Atom, pretty good. Muon into Atom, bad. Atom into Muon, oh, this is lost, my bad. Wait, no, this is on eval scores, yes. Atom into Muon is still good. I don't think it's uniformly good across all benchmarks is the reason. And yeah, Muon into Atom is the worst. Okay. It doesn't stop us from trying though, because you can still do some tweaks like extending Muon to Schatten norms, or you can like the problem of the fine tuning and training mismatch is not completely understood, because technically the operator norm training with Atom and training with Muon should be exactly the same. So why does it not work as well as Atom for both cases? So it might have to do with initialization. And yeah, we can also extend Muon to include all parameters. And this involves finding the operator norm for all of the operations inside of a neural network, and then designing a custom iteration scheme for that algorithm. So conclusions. Muon is an optimizer which cares about norms. It's 2x faster than Atom on transformers. It doesn't require much tuning, and it's only used for linear layers. But the core trick, which is thinking about norms, it works generically. And yes, you could also move the field forward, because this only exists for linear layers, doesn't exist for embeddings, doesn't exist for comms, doesn't exist for fixed point operators, right? It's like,
Well, they just a sequential linear person.
is there a different norm if you take the fixed point version? It might be, right? Or not?
Probably, I don't know.
Yeah. I'm assuming that if you look at it from the perspective of the full fixed point iterated, then it might have a different operating norm. So, questions? There's free questions also.
It's like the main feature of it is that they try to scale the updates so that the activations do not go over some threshold, and it kind of helps.
It actually slightly changes the absolute direction of the gradient.
Yes.
Yeah. So the rescaling happens in all directions, not just in one direction.
And did they look at the weights of the training model? Does it like produce more uniform weights?
Oh yes, it does. So an interesting result is that it produces better weight erasure. Yeah, so Atom actually keeps things relatively within the initialization range here. Yeah, so without dualization, the weights don't really change much over the process of training. And as a result, they don't achieve as good of an accuracy as it possibly could. Versus if you do dualize your gradient, which is that Newton-Schulz iteration thing, the weights disappear rapidly. And then it achieves better training accuracy.
I didn't get it, sorry. What do you mean by weights disappear?
They're watermarking the gradient, or the watermarking the weights. So they're writing the letter A into the weights at the start, and they train one model with including dualization, which is that Newton-Schulz iteration process, and they train a different model where they do that dualization, where they're iterating, they're doing the Newton-Schulz iteration. In the Newton-Schulz case, the weights diverge from the initialization much faster.
Okay.
Which means that they're potentially more expressive, versus the non-dualized version, which stays roughly within the same region.
I wonder the effect of that on the predictability of, like, you train on the start and blah blah blah.
I've seen people suggest that, like Kimi. If anyone here used Kimi before, Kimi K2.
Actually, I wasn't impressed.
It's an exceptional writing model. It's not that great of a programming model. It's a really good writing model. It's extremely creative. And people were suggesting that it was because it was stripped with Muon. It's the only large model stripped with Muon. That's why its personality is so weird. The way that I've described it is that Kimi K2 is like if Batman had a kid with Dostoevsky. It's like extremely poetic, but it also only drops one-liners all over the place. Very strange model. I love it. But yeah, people are suggesting that it's because it's trained with Muon. I don't really buy that, but it might be the case.
It's the only model trained.
It's the only very, very large model, like practical model training.
Oh, you're doing it open router?
It's on a router.
Yeah, that's how I used it. But yeah.
Yeah.
I don't remember anything.
Okay. So Any more questions?
One of the three questions, if I can gather. From you. I didn't get the fine-tune pre-training scratch at all.
Yeah, this is or do you not understand the discrepancy or why it's there?
Yeah, like you pre-train with one and then fine-tune with another,
Mhm.
and if you pre-train with Muon and fine-tune with Adam, it performs doesn't perform as well, or what?
Let me
Yeah, maybe we can hide this story just.
this guy somehow is. Okay. Yeah, if you do Muon with Adam,
And you need to put your mask on and ask question. To end up on the record.
yeah, on MMLU, Muon into Adam performs worse. Adam into Muon is bad. Is worse than Muon.
No, but a little.
Yeah, only a little
So
bit.
why is that? And the stable is not useful because they don't show, well, it's fine-tuned model. How do I judge if Adam Muon dropped from Adam? That's impossible, right?
Adam Muon dropped from Adam. What do you mean?
Well, like how much change starting, like how much did fine-tuning with Muon change the weights?
Oh, I see. Yeah, the delta.
Like what is happening there? And especially given that Adam keeps the motor marking, so it kind of stays. And I like, yeah, it just learns. I guess Adam kind of learns to ignore. Adam is more holographic or something. Like it learns to ignore this zero weights, right? In the like, okay, it's just like okay, I can't do.
Right.
And that's why we need to immersion. Probably with Muon, we can deal with much smaller ones because we are not like that sensitive, that hungry for large parameter space.
Mhm.
Because like clearly, if Adam can't change values that much, like you gave it a large chunk by chance that it's zero, and it's dealing with those little parameters around that example. I never thought about it. It's just like the first thought about it before. I mean, it's just the first time I think about it. Yeah, we need larger spaces, not because smaller models cannot perform, because we cannot optimize smaller
Right.
models.
Mhm.
So it feels like Muon potentially can optimize
Much smaller models.
to better accuracy.
That would be very interesting. Yeah. That would be very interesting.
Okay. Anyways, thank you, Mike. This is fantastic.
Thank you very much for coming.
I have more questions and stuff, but I don't know if people are Halloween hungry friends. Are we celebrating now at Dima or something?
There is no, it's a virtual talk to them.
Oh, okay. It should be Halloween then. So, thanks for watching us online people.